Hey guys, welcome. In this lecture, 15.3, I think, we'll be talking about sequences of functions and integral. I would like to relate the sequences of functions with integrals. Especially, we would like to answer the following question. How can we pass to the limit inside the integral? So basically, when we deal with a problem, let's say, finding the limit of some integral, and we have inside the integral some sequences of functions, we would like to swap the integral with the limit because it will be easier for us to deal with the limit of the sequences of functions. But before we go into that, I would like to talk about sequences of functions. And here we will dwell on something which is very important. Since we talk about the limit, we would like to talk about the convergence. And there are two types of convergence that we will be talking about. The first one, which is the normal convergence, which we will call the pointwise convergence. And the second one, which is a little bit more, a little bit more involved, I would say, is the uniform convergence. All right, so let me start with some basics about the sequences of functions. In fact, I will just do a crash course in advanced calculus. And now, let's talk about first about sequences of functions. So, and here we would like to talk about convergence. And we said that there are two types of convergence with, well, the two more important types that we will deal with. The first one is the pointwise convergence. And the second one is a uniform convergence. So first, let's recall the following definition. And here, this will be about pointwise convergence. In fact, I will give the definitions with epsilon and, and then we will see which one implies the other one. We'll see a bunch of examples and so on. In fact, we will see a sufficient criteria for pointwise convergence to imply the uniform convergence. But anyway, we'll go there. First, let's start with the definition. So let us consider a sequence of functions. So let's fn n greater or equal than 1. And anyway, let me define this on a closed and bounded interval AB. And this will be a real valued sequence of functions. So be a sequence of functions. All right, so we say that Fn, let's say, converges pointwise to the function f, right? And we'll denote this in this way. So we write this fn converges to f as n approaches infinity, right? If, I'm going to write the definition, if for all x in 0, 1, in AB, sorry, and for all epsilon positive, right, there exists a rank, let's say, n epsilon of positive integers, such that for all n greater than n epsilon, we will have that fn of x minus f of x in absolute value is less than epsilon. So that's what we mean by pointwise convergence. So let me put it like this, PC. So that's what we mean by pointwise convergence. All right, now let's write a definition for the uniform convergence. And we will like to see the difference between the two. So now, in the same way, let me consider Fn, a sequence of functions, be a sequence of functions we say that Fn converges uniformly to the function f right? And we're going to write this in the following way. We're going to Fn will have two arrows here. So this will mean that Fn will converge uniformly, right, to f if, and now I'm going to write if for every epsilon positive, right, there exists a rank n epsilon such that for all x in AB and for all n greater than n epsilon, right, we will have that Fn of x minus f of x in absolute value is less than epsilon. So that's what we mean by uniform convergence. And I'm going to denote this by UC. So as you can see, the notation for pointwise is this one, and the notation for uniform convergence will be this one. I would like you to look at the two definitions, and you'll see that there is a slight difference, well, between these two. So what is the, so let's answer this question, because this is a very important question, right? So let me just stare at this for one more, for a couple more seconds. As you can see, the pointwise convergence, if you look closely at the two definitions, basically it says that the first one, right, for all x and all epsilon. So basically, if we look carefully, you will see that the pointwise convergence, the rank, depends also on epsilon and for the specific values of epsilon and x. So actually, let's write this down so that we can make things clear. So the question is, let's say question one, what is the difference between pointwise and uniform convergence? That is the question, first question that we would like to answer. All right, so let's start with the pointwise convergence. So for pointwise convergence, let me the rank, let's say n epsilon, right? This guy, and we will write it in this way: n epsilon nx, Let me write it in. So this rank may depend on both epsilon and x. Right? And the choice of n epsilon of the rank only has to work for specific values of epsilon and x that are given. Hope this makes sense, right? So the choice. So that's the pointwise convergence. So the rank may depend on both epsilon and x. Well, in the case of uniform convergence, well, this rank can only depend on epsilon, so we don't need x anymore. So let's write it. The rank n epsilon, and I'm going to write it in this way, as n of epsilon, and that's it, can only depend on epsilon. And the choice of n epsilon has to work for all values of x in AB. For a specific value epsilon that is given. All right, so that's the difference. At this point, probably it is, I hope it's quite clear that we can distinguish between the two. And now another question, well, how these two are related? Well, it's pretty much obvious at this point that uniform convergence implies pointwise convergence. So let me point out this remark by just looking at the definition. Uniform convergence, so UC implies pointwise convergence, but not the other way around though. They're not equivalent. So pointwise convergence does not imply uniform convergence, and the counterexample to that, counterexample is the following. So let me consider this sequence of functions. Fn defined on 0, 1 closed interval, real value. Fn of x is x to the power n. Well, clearly, this will converge pointwise. So this converges pointwise to this function f of x, which is given by 0 if x is between 0 and 1, open at 1, pay attention, and 1 at x equals 1. Well, there is a property that since this guy is, if Fn would converge uniformly, right, to F, right, then since this guy is continuous, uniform convergence will transfer all these, so this guy is continuous, is a sequence of continuous functions. Well, by uniform convergence, the continuity will be transferred to F. But this, unfortunately, if you look at this piecewise continuous function, this is not continuous. So therefore, we get the contradiction. So as you can see, there exists a counterexample to this. There are plenty of other counterexamples for the fact that the pointwise convergence does not imply uniform convergence, but this is the easiest one. You can come up with plenty of other counterexamples. All right, but now, well, like I said, I don't want to go too much in giving you a crash course in basic real analysis or advanced calculus, whatever you want to call it. But I need these notions because I will use them in problems. And in fact, I would like to see how uniform convergence will behave towards passing to the limit inside an integral. So this is what I want to get to. All right, but before we go into that, well, since we said that the uniform convergence implies pointwise convergence, and we said that the vice versa, that's not the case. Well, we are wondering, is there like a sufficient condition, or can we add a condition such that from pointwise convergence we can obtain the uniform convergence? Well, there is this criteria, we will call criteria for uniform convergence. Criterion for uniform convergence. And this is pretty cool because it will give you a very precise way of dealing with once you have pointwise convergence, and there will be a if and only if condition to obtain uniform convergence. So let us consider a sequence of functions, and let's just say again, define on a closed and bounded interval AB, real valued, be a sequence of functions. All right, great. And we say that then Fn, let's just write in words, and converges uniformly to F, right, to let's say to a function F defined on AB and real value, if and only if, so I'll write it in this way, if and only if, and probably you are used with my notation so far, I will write this as if with double F. If and only if, we have this, that the limit, like, let me write this condition with as n approaches infinity of the supremum of x in AB of Fn of x minus f of x in absolute value, right, is 0. All right, so this is the condition. Right? In other words, if we have a function that converges pointwise, right, to let me write it again. So in other words, you have the following: Fn converges pointwise, let's say to a function f, and the supremum of when x is in AB of the absolute value of Fn of x minus f of x goes to 0 as n approaches infinity, then definitely these two will guarantee that Fn will converge uniformly to F, right? So that's what that's pretty cool criteria. So that's what you need to know. So now when you have examples of sequences of functions, you take a look at the supremum. When you evaluate the supremum, well, there are pretty standard methods to evaluate that. And then when you take the limit as n approaches infinity, then and the limit gives you 0, then definitely this will guarantee you the uniform convergence of the sequence Fn. All right, that's great. That's absolutely great. So keep in mind this condition here. This is an important condition for uniform convergence. All right, now, well, what happens so let's answer the following question. I don't know, question number 2, I think, right? So question 2. Does uniform convergence give us that, let me write it like this, the limit of the integral is the integral of the limit. So let me write this generically like this. So that is the question. And the answer is yes, it does. Indeed, it gives us, we can do that. So we can swap the integral with the limit. So let me just write the theorem. This is a very important theorem. So basically the theorem says the following. So again, let Fn be a sequence of functions, right? Defined on again on the interval AB. And I would like to say, let me be more specific, of integrable functions. This is important, right? And F defined on AB is a function such that we have the following. We have that Fn converges uniformly to F. Right, so this, let me write this again. Fn converges uniformly to F. Then, guess what? We have the following, that the limit as n approaches infinity of the integral from a to b of Fn of x dx is nothing else than the integral of the limit of Fn of x dx, and since this converges uniformly, this will be nothing else than the integral from a to b of f of x dx. In fact, I should say that maybe then f is integrable. And moreover, we have this. And this is a very important equality here. In other words, uniform convergence will guarantee that I can swap the integral with the limit, which is pretty great. I mean, so that's what we call, this is also called, maybe I should have said, this theorem is called the uniform convergence theorem. Right. So as you can see, the uniform convergence theorem is pretty strong, right? Well, but I'd like to point out a remark here. The uniform convergence theorem is pretty much a very restrictive condition. So if I want something to converge uniformly to a sequence, if I want a sequence of functions to converge uniformly to a function, that's a pretty, I'm a very pretentious guy. So since that it's a pretty restrictive condition, to be honest with you, in many situations, that's not even valid. Well, we ask ourselves, in fact, let me ask this as a question. Does the uniform convergence theorem still hold true if we have only pointwise convergence? So instead of uniform convergence, we would like to replace that with pointwise convergence. So that's a natural question, very natural question that we can ask. Well, as you can imagine, if we assume only pointwise convergence for Fn, then the theorem is not gonna, it's not valid anymore. So everything will not hold water. So basically, so the answer is no. And let me give you a counterexample. I don't want to deal too much with this, so maybe I'll leave this to you. So let me consider this. So let me consider this sequence of functions. Again, I'll define on 0, 1 and real value. So I want something that, and let me just take this. That's a pretty standard example. So maybe oh, great. So I'll take something like nx e to the power nx squared, let's say. Yes. All right. So one can compute the limit. So at one hand, one can compute that the limit of the integral, so the lim as n approaches infinity of the integral from 0 to 1 of fn of x dx. So once we deal with this, this would be the lim. Oh my God, let's do it. Nx e to the negative x squared dx. Oh, right. So let's see here. Actually, I can compute this. So this would be the lim as n approaches infinity. So the antiderivative of this will be negative e to the negative nx squared over 2, I think. Yes, from 0 to 1. So here we use the fundamental theorem of calculus, and this would be, if we put there, so this would be 1 e to the negative n squared 0, 0, 1. So, okay, so it will be the lim as n approaches infinity of 1 minus e to the negative n over 2, which this gives us 1/2. Great. So on one hand, we have this guy here. So if we compute the limit of the integral, and now guess what? On the other hand, in fact, we should have said, we should have pointed out this in the first place. So on the other hand, if we take the limit as n approaches infinity of fn of x, right, which is nothing else than the limit as n approaches infinity of this guy nx e to the negative nx squared. So if we take the limit of this guy, so this would be what? This would be 0, right? It's actually pretty obvious. That's 0 for all x in 0, 1. All right, great. All right. So what do I want? So the integral, let me compute of the limit of fn of x, right, dx, this guy is, guess what, is 0. Well, as you can see, the two values are not equal, right? You have here 1/2, here we have 0, and this guy here, this is the integral of the limit. So the limit of the integral is not equal to the integral of the limit. So there you go. So you see, this is a sequence that doesn't converge uniformly. I'll leave this to you as an exercise, but that indeed does converge pointwise to the function f of x equals 0 on the entire interval 0, 1. Anyway, you can come up with plenty of other examples, and I'm sure this could be done in like a standard basic real analysis course, but I don't want to deal with this too much. All right, so at this point we have the uniform convergence theorem, which is a pretty strong tool. So once again, when we have a sequence of functions which is uniformly convergent, so then we can swap the integral with the limit, which is great. All right, but now we would like to see under, like I said, this is pretty restrictive, right? So uniform convergence. Now the question is, can we add another condition? So again, we would like to deal with to come up with a similar theorem as the uniform convergence theorem, but I'm still insisting in dropping out the condition of the uniform convergence of the sequence of functions. So in other words, as you have seen, if I drop out the uniform, so if I just replace the uniform convergence with pointwise convergence, the theorem fails. That's as we have seen in this counterexample. But now the question is, what if I will add an extra, so I will just keep the pointwise convergence, but I will add some extra condition that will guarantee, which will not imply uniform convergence, but it will be enough for me to guarantee that I can swap the integral with the limit. So the question is, can I do that? And the answer is yes. And this is what we will call, I'm veering towards something which is very strong theorem, which will be called the dominated convergence theorem. Usually that is taught for more measurable functions, and you can learn that in a real analysis course, measure theory course. But before I go into that, let me just give you a version of the dominated convergence theorem, but for Riemann integrable functions. And this is what we call the bounded convergence theorem of Arcella. So theorem don't recall Arcella, okay, like this. And I think this was given around, I don't know, 1885, if I recall the year. It's a pretty amazing theorem. Like I said, I will give you after that a more general theorem, which will be called the Lebec dominated convergence theorem. All right, so the theorem says the following. Let Fn be a sequence let me just write it in this way. be a sequence of integrable functions all right, and now such that Fn converges pointwise to F, and F is also let's say Riemann integrable. All right, so nothing special so far. Riemann integral on the interval AB. So far, it's just common sense. But now here comes the extra condition. If there exists a constant let me write like this. Let's just say M, right? A positive constant such that Fn of x in absolute value is less or equal than this constant for all n and for all x, right? Then indeed we can pass the limit inside the integral. So then we have the limit as n approaches infinity of, how did I write it? Let me see. Okay. Of the integral of Fn of x dx. This is the integral and moreover, this will be the integral of a to b of f of x dx. Wow, that's great. So I keep the pointwise convergence, but then I add this extra condition here. This one here. So I bound by a constant the sequence of functions. So that's why we call this the bounded convergence theorem of Arcella. Sometimes it's called the weak version of the Lebec dominated convergence theorem, because that would be a little bit more general. But that's a very strong theorem. As you can see, I don't need uniform convergence here, so that's great. But if I can bound my sequence of functions in absolute value by this constant m, then I'm good to go. So I can pass the limit inside the integral, which that would be great. Okay, now let me veer towards a little bit more theory. I'd like to talk about now about negligible sets. And in fact, I would like to give you a two other theorems like this. In fact, I would like to give you the monotone, to talk about the monotone convergence theorem, the dominated convergence theorem, and in fact, I will include this bounded convergence theorem of Arcella as the weak version of the dominated convergence theorem, right? In fact, let me say that this theorem, the bounded convergence theorem of Arcella, will be just a special case, well, a particular case, if you want, of the Lebec dominated convergence theorem. But before we go into that, let me recall another definitions. So definition, God knows what number it is, I forgot, but anyway, it doesn't matter. So we would like to talk a bit about, well, negligible sets, or so that I wouldn't mention like I said, I don't want to go too much into measure theory. So I want to mimic this by just sticking to Riemann integral. So let's say a set, well, actually a subset, a set A, let's say a subset of R is called negligible So we say this is negligible if for any epsilon positive, there exists a sequence of open intervals let's say let's call this like this, A and Bn, right? Such that we have this condition, right? So this is A will be in the union, the infinite union of these intervals. And the series is less than epsilon, what's the difference? Okay, so that's what we call a negligible set. Well, as an exercise, one can prove, well, if we talk about countable sets and so on and so forth, one can prove that the countable set is negligible. And also, but not the other way around. For example, you can take the Cantor set, you can play around with it. This is actually a pretty standard exercise in real analysis. So I'll not go into that. But there exists this important theorem, which says that if I have two, basically this theorem says if I have two integrable functions, let's say f and g, and they're equal for all x except a negligible set, then their integrals are equal. So in other words, let's say let f and g be two functions and the set A, a subset of R, is negligible set. Such that f and g are equal for all x in A, B minus set A. Then their integrals are equal. Then the integral of A of f is the same as the integral of g. All right, great. So I don't care about negligible sets. I take them out, it's fine. All right, and now let me veer towards a very important theorem. And this is what we call the monotone convergence theorem. If you want, this is more like a, the integral version of the classical monotone convergence theorem, right? Remember the monotone convergence theorem? Every monotone and bounded sequence is convergent. But, well, in that case, in the case of sequences, I only talk about one convergence, well, which is the pointwise convergence. There's also the uniform convergence and so on. So I just deal with sequences of real numbers. All right, but here we have the following. So let Fn be a sequence of functions, and let's just say okay. all right, be a increasing sequence, let's say, of integrable functions that converges pointwise, that converges pointwise to an integrable function f. Right? All right, great. Then, guess what? We can have the same thing, the limit as n approaches infinity of the integral from a to b of fn of x dx. In the end, we can pass the limit inside, so that would be the integral of the limit of fn of x dx, and this will be the integral from a to b of f of x dx. All right, that's great. So that's the monotone convergence theorem. Right? We have an increasing sequence of integrable functions that converges pointwise. This is important, to an integrable function. So once we have this, then definitely we can pass the limit inside the integral. And there is one more theorem that I would like to talk about. And this is what we call theorem Lebec dominated convergence theorem. This is one of the cornerstones of a real analysis course. When you will learn it, you don't learn this in a basic real analysis, but in a real analysis course, you'll learn about the Lebec dominated convergence theorem. And all right, I'm gonna put it in this way. As you will see, and I'll relate this to Arcella's bounded convergence theorem. You will see it's a little bit different. All right, so in this case, we have, so let Fn right? This is a sequence of functions, right? Be a sequence of integrable functions. All right, such that Fn converges pointwise to f. And this guy f is also an integrable function. And now I'm trying to generalize a bit, right, the bounded convergence theorem. So, and now consider a function g, right? So let a function g be an integrable function as well. All right, great. Such that, and these are the two conditions that are very important, such that Fn of x in absolute value will be less or equal than g of x, right? And moreover, the supremum, right, of this set, let's say of the integral of g, right? This set is finite, right? So the supremum cannot be infinity. Well, guess what? The same thing will happen. Then we can pass to the limit inside the integral. So in other words, we have that the limit as n approaches infinity of the integral of f of n of x is the same as the integral of the limit and is the integral. That's it. Wow. Well, I want you to look at this Lebec dominated convergence theorem for a bit and to see the difference between this one and the bounded convergence theorem of Arcella, right? As you can see, in the case of Arcella's theorem, the function g was a constant, and the constant has to be finite. So in other words, if we take g to be m, Lebec dominated convergence theorem is Arcella's bounded convergence theorem, right? So let me point out this remark. If g of x is constant m, right, then dominated convergence theorem is the bounded convergence theorem, right? Let me just look at the statement of the bounded convergence theorem of Arcella, right? As you can see, I have the constant here. So I have a constant, which of course cannot be infinity. And this condition that Fn in absolute value is less than or equal than that constant. So, but in the case of the dominated convergence theorem, we have a function, g of x, doesn't necessarily have to be a constant. We have a little bit more general in the case of the Lebec dominated convergence theorem, right? As you can see here. All right, great. Now I would like to do a bunch of applications because I've done too much theory, and I like to do applications, and this will be very important. And in the recitation section, I'll do even more applications, but I'll just want to do maybe 2 applications now, and I'll save some more applications for all the following lectures. All right, so the first application, let's say this is a very classical problem. So let's say problem 1. This is I don't know, it's at some point in the recitation, I'll solve a problem given in the Putnam competition, which will be just an application of this problem. This is pretty well known. It's a pretty famous problem at this point. It's usually given at the Berkeley preliminary exam. But not just Berkeley preliminary exam. All over the place, even when I was a graduate student at the University of Pittsburgh, this problem usually appeared pretty often. Well, of course, it has an elementary solution. Solution is not just by using more advanced stuff such as the dominated convergence theorem. Okay, the problem says the following. So let f be a function. So f is defined on 0, 1, real valued. be an integrable function that is continuous at the point x equals 1. Then show that the limit as n approaches infinity of the integral from 0 to 1, in fact, n x dn times f of x dx is f of 1. This is a very it's a classic at this point. Well, usually the elementary solution, you can break the integral because we have problems at 1. So we would like to avoid 1. So we would like to split the integral from 0 to epsilon, and then to epsilon to 1, and then we can take that quantity, which around 1, we can get rid of it by some miracle, and then we'll deal with only the first integral. And so that's the pretty much the classical approach. But this could also be seen as a standard application of the Lebec dominated convergence theorem, and let's solve it in this way. So as you can see here, we have to be a little bit careful though, because we have to be precise with the solution here. So let's come up with a change of variables. So we perform the following change of variables, or U sub if you want. Let's say x to the n equals u. So we have this. And now, we would like to express this integral, right? This quantity in terms of the new substitution, right? So we have, let me just do a computation. So n x to the n minus 1 dx du, right? In fact, okay, it's pretty easy to write it. So in other words, this implies that the limit, in fact, I don't need to pass the limit yet, that the n times the integral from 0 to 1 of x to the power n of f of x dx. So this guy here will be equal to, if we are careful, so n x to the n x, so this will be the integral from 0 to 1 of the nth root of u times f of the nth root of u du. So we would like to look at this guy here inside this sequence here. Let's denote this by fn of u. And we would like to apply the dominated convergence theorem to this. So we want to apply, so the goal is to apply the dominated convergence theorem to fn of u. All right, but first let's see the point, the limit of this. So the lim as n approaches infinity of fn of u is the lim as n approaches infinity of this guy. So the n root of u times f of the n root of u. All right, so this guy, if we look closely, since the function is continuous at 1, let's not forget about that piece of information. So this would give us, pass to the limit here, since continuous at 1, so this would be f of 1. That's pretty obvious, right? For all u in 0, 1, right, without 0. And okay, and we should be careful here, and the limit as n approaches infinity, that's why it's important to be careful with the details in this case. At 0, when u f of fn of 0, this will be nothing else than just 0. Well, we don't care about this. The set, since the set formed by the element 0 is negligible, so we don't care. We can it's just a finite set formed by just one element. Then by the dominated convergence theorem, what do we have? So we have that the limit as n approaches infinity of the integral of fn of u du is nothing else than just the integral of the limit as n approaches infinity of fn of u du, but since that's negligible, so this would be the integral from 0 to 1 of f of 1 du, but this is nothing else than just f of 1, and that's it. Game over. So that's the problem, right? As you can see, it's just a simple application of the Lebec dominated convergence theorem. In fact, I would like to point out some remarks here because you might fall into a trap with this example. And in fact, you can play around with many other examples of this type. And in fact, I'll give you one and I'll leave it to you as a homework to have fun with. So let me point out some remarks here. So the first remark that I have in mind is the following. All right, so let me go back to the initial. You see, maybe if I don't have this idea of applying this change of variables or u sub, maybe I can do, what if I want to just go directly? So what if I consider this function? So the question is, can I apply the dominated convergence theorem directly to the function? So the answer is no. So we cannot apply directly the dominated convergence theorem to the sequences of functions fn of x, and we'll consider like n x to the n times f of x. We cannot do that. Well, we cannot do that, although the sequence of functions converges pointwise at 0 on the interval 0, 1, right? Open at 1. But we cannot apply the dominated convergence theorem, unfortunately. Well, for obvious reasons, because I cannot even bound this by a function, so such that the supremum is less than infinity. So it's not productive for me to do such a thing. So it's better to to do a change of variables, right? And a second thing, since we talked about the change of variables, right? Well, it's correct, right? Well, maybe I don't want to go too much being very pedantic here, but well, the change of variables, when we do basically the change of variables of the U sub or the U sub, right? It's actually when we do this change of variables, so basically x is so x to the n is the square root. So basically the function phi of u, right, is u to the power 1 over n. So this. So when we perform this change of variables, this function is not differentiable this function is not differentiable at 0, right? So since this is not differentiable at 0, if we want to be more pedantic, we can just consider the change of variables on, let's say, away from 0. So so we can consider the change of variables or the U sub on only on the interval epsilon 1, right? So away from 0, and then, well, pretty much is the same thing, but if we want to be like very precise, and then we obtain, let's see, what do we obtain? So if we obtain something like, well, n, the interval from epsilon to 1 of and so f, this would be the interval from epsilon to the power 1 over n to 1, right, of u to the power of the n root of u times f of the n root of u du. Okay. And then we can take the limit and then take the limit as epsilon approaches 0 from the right. And of course, if we want to be very precise, just like I said, we can do this kind of justification. All right, so this is a pretty standard problem at this point. Like I said, if you wanna, you'll find it in pretty much in every textbook. I think you can even find it in both Rudins, baby Rudin and real analysis Rudin. So in both principles of mathematical analysis and also in real and complex analysis. It's a pretty standard exercise at this point. And just like I said, I will show you an application later on, probably in the recitation. I will show you a Putnam problem, which will be derived directly used from this problem. So it's a pretty nice problem to have in mind. Of course, you can modify this problem. You can tweak it a bit, and you can just, for example, I will leave this to you as a homework because I don't have time or more time to solve this, but it's just the argument is pretty much the same as in this one. So let me just mention this. So a similar problem. So a similar problem. So again, I have a function, so let f defined on 0, 1 be an integrable function that is continuous at the point that x equals 1. Show that the limit as n approaches infinity of, so let's modify this a bit, and the integral from 0 to 1 of x to the n times, so the problem, this problem was f of x, let me see. Okay, and now I'm just going to put f of x to the n dx. So let's see, this will give us what? Okay, so that would be actually the integral from 0 to 1 of f of x dx. So try to play around with this one. Like I said, the arguments are pretty much the same, and like as in the previous problem, right? So it's basically the same. You just perform the same U sub, and then you apply the dominated convergence theorem. But anyway, I'll leave this to you as a homework. And now I have one more problem in my mind, because I would like to do this problem. It's a pretty standard prototype as well. And in this problem, we will deal with the characteristic function of a set. And after this, I think I'm going to stop, and you will see plenty of other applications in the future lectures and recitations. So, problem. Not sure if I recall it correctly, but this is pretty standard in harmonic analysis textbook. But anyway, so let f be a function. So be a continuous function. Show that that the limit as n approaches infinity of the integral from 0 to 1 of f of x over, let's say, nx squared plus 1 over n. Well, I modified a bit, so this would be pi over 2 times f of 0. Okay. Again, we would like to apply, as you can see, I have the limit of the integral, so the ideal scenario for me would be to apply the dominated convergence theorem to this integral. So basically, we would like to swap the limit with the integral. So, but we would like to do something here, and we should be careful a bit. So let's see. Should we do? So let's rewrite this a bit, right? Let's perform again a change of variables, and okay. So we can perform a change of variables. So we can take. So we have this integral. So this would be, if we perform the following change of variables, let's say nx equals equals t, let's say, right? equals u, sorry, let's u as a u sub. So n dx is du. So when x is 0, u is 0. And when x is 1, u is n. Aha. All right. So this guy would be, and pay attention because this would be a bit tricky, the integral from 0 to n. So far I didn't take the limit, so bear with me. Here we have that nx, so this is n dx. So this would be f of u over n here on top. And on the bottom, we have u squared plus 1 du. Great. So I have a new variable. And now we should be careful here. So this guy, if we want, we can express this when we pass, well, when we pass to the limit, right? If we take this sequence of functions, so if we consider this guy here, this is fn of u, right? But not quite. We should be careful a bit because I like to do something. And I want to be careful here. So this guy here can be written as, so if we pass to the limit, okay, I can express this as the integral from 0 to infinity of f of u over n over u squared plus 1 chi 0 n of x, of u, sorry, du. So this guy is the characteristic function. So let me write it here, chi of 0 n of x. This is nothing else, right? Is the characteristic function is 1 if x is in 0 n. So if x is between 0 and 0 if x is greater than n. It's not in this interval, right? So in other words, I can consider now this sequence of functions, right? Look at this guy here as my fn of u, right? And this guy, I would like to apply, so we would like to apply the dominated convergence theorem to the sequence of functions to fn of u, which is given by this, f of u over n over u squared times chi of x on 0 n. All right, remember the dominated convergence theorem? Now the question is if what kind of function should we take here, right? So we're looking for a function g. So in other words, we're looking for a function g of u, which will be, let's say, we can bound this since this bothers me, f of u over n. So since f is continuous, it's bounded. So I can bound this by, let's say, an m, by the supremum, the maximum of f. Let's say u squared plus 1, right? Where m is nothing else than just the maximum when x is in, when u of f of u. right? So I have no problems now to apply the Lebec dominated convergence theorem, right? So therefore, this would be, so by the dominated convergence theorem, we have that the limit as n approaches infinity of the integral from 0 to n of f of u over n over u squared plus 1 times du is nothing else than just okay, let me put it like this. The limit as n approaches infinity of the integral from 0 to infinity of f of u over n over u squared plus 1 times chi of x, 0 of u, sorry, du. And this guy will be the integral from 0 to infinity of the limit here inside will be f of 0, f is continuous. So it will be f of 0 over u squared plus 1 du. This guy will be f of 0 over the integral from 0 to infinity of 1 over u squared plus 1 du. And this guy is arctan of, so that would be pi over 2, right? So this would be f of 0 times pi over 2. And that's it. So as you can see, I wanted to do this application because it involves, well, as you can see, the integral from, when we do the change of variables, we have the integral from 0 to n. And then you can write this integral in terms of an improper integral, which I haven't talked about, but I will. So the next lecture will be about improper integrals, and you will see exactly how to deal with these. Anyway, I just touched the subject a little bit right now. We will be, next lecture, we'll be talking about absolute convergence, absolutely convergence, convergent integrals, conditionally convergent integrals, and so on. You will see that absolute convergence will imply conditional convergence, but not the other way around. So I'll be talking about improper integrals. You'll see examples, but also there will be a version of the dominated convergence theorem for improper integrals. So, but anyway, I just wanted to do this example so that you can see a little bit, to give you a little bit of a taste of what the improper integrals are all about. All right, I think I'm going to stop here for this lecture. Like I said, this was just talking about a little bit about sequences of functions. And in fact, as you have seen, I was interested more in how to deal with integrals of sequences of functions. And through the course of this lecture, I think you can you got the main idea on how to deal with these limits of integrals. You will see, like I said, next time I will talk about improper integrals, and probably that will be next lecture, and then in another lecture I'll do plenty of applications. But then the recitations will follow, and then you will see plenty, many more. All right, guys, I think I'm going to stop here. Thank you very much.